Hey everyone, welcome to our deep dive into our gunshot detection system. My name is Max.
And I'm Manav. Today we're excited to walk you through how we built a life saving system that can detect gunshots in real time and alert local authorities instantly.
So it all started with heavy inspiration. In 2021, the Oxford High School shooting happened, which was unfortunately less than 20 minutes away from our own school, and it hit our community hard. We realized that in emergencies like these, every second counted. After all, some students can't call the local authorities for fear of being hurt. And so we thought if there are fire and smoke alarms, why not gunshot detecting alarms? Why not create a system that automatically detects these gunshots and gets help there fast?
Absolutely. We wanted to design something that was not only technically sound, but also practical and affordable. The idea was to integrate state of the art machine learning models with reliable, low cost hardware. Our goal was to develop a device that could be used in all community spaces, not just schools, such as churches, grocery stores, and more.
And from a software perspective, it's not just about detecting loud noises. Our model needed to distinguish between similar sounds like popping balloons or the dropping of books. That's where our custom architecture, the SECRNN, came into play.
Now, let's switch gears to hardware. There were three main components and factors that we considered during our designing phase: efficiency, functionality, and affordability.
I remember you mentioned that we had to iterate through several prototypes, right?
Yeah, the first step was to design a compact casing system that could house all of our components, which is the microphone at the top right here, a USB microphone, or a USB speaker that's right here, and a Raspberry Pi 4 that's inside the casing system itself. So using Onshape, we started with several different CAD models to figure out the optimal configuration of all these components relative to each other. One of the early lessons that we learned was about the microphone placement. Originally, the entire module was flipped upside down, with the microphone being below the entire system. But we realized that the audio quality was subpar, so we moved it to the top of the module, giving the entire system that you see today.
That's sick. And keeping costs low was a huge priority, right?
Yeah, so we had a strict budget of $300, and to hit that target, we experimented with various 3D printing materials since this entire system is 3D printed. Originally, it was TPU filament, but since it's more expensive than other filaments out there on the market, I switched to a PLA filament, which is much more cost effective. The infill density was also fine tuned to strike a balance between durability and material usage. And ultimately, we created this robust, affordable product that doesn't compromise on performance.
So, how can you prevent spoofing attacks, though? In other words, how can you ensure that false gunshot sounds played from a different audio source aren't classified as real gunshot sounds?
Yeah, that's a great question, Max. So we've developed a mobile app that's fully live and functional right now, and it's built using React Native, which can run on both Android and Apple devices. Every gunshot detection alarm is uniquely linked to this app. So, when an alarm detects a potential gunshot, it immediately notifies all nearby users who on the app are connected to their respective alarm. And correspondingly, the local law enforcement is alerted as well, and all detection logs are stored in Google's online cloud database called Firestore for future reference and for law enforcement to use. So, going back to your question on spoofing attacks, our app features a confirmation system which requires only a few users to confirm that there's an ongoing threat alongside the machine learning model receiving a detection.
The heart of our system is the SECRNN, which is built on a convolutional recurrent neural network.
First, though, Max, can you explain how we pre-process our audio data and why we chose this method?
Absolutely. In most audio event recognition systems, the raw audio is first transformed into a spectrogram. A common approach is to use MEL filter banks, which converts the frequency access into logarithmically spaced MEL bins. This mimics human hearing, but it comes with a trade-off. The time frequency resolution is reduced. For instance, while MEL spectrograms work well for a majority of sounds like human speech, they tend to saturate when dealing with high-intensity events such as gunshots, losing key discriminatory details.
Right, and that loss of detail can really hurt detection accuracy when every nuance matters.
So when we saw that most state-of-the-art methods use these methods, we decided that we could try something better. That's why we experimented with short time Fourier transform, or STFT, for pre-processing. STFT is a separate method that divides the audio signals into overlapping segments and applies a discrete Fourier transform on each segment. This method retains detailed spectral information and significantly reduces spectral leakage, even in the face of oversaturation.
So, STFT allows us to precisely adjust the balance between time and frequency resolution, which is crucial for capturing short duration, high intensity nature of gunshots.
Exactly. By using STFT as our pre-processing method, we ensure that our model receives a more accurate representation of the audio signal. This in turn boosts the performance of our actual machine learning model later on, letting it distinguish from other high saturation sounds. So after pre-processing this data, obviously we need to train a model. And after testing, we noticed that the convolutional recurrent neural network performed heads and shoulders above other architectures.
Yeah, so the CRNN combines CNNs and RNNs to extract both spatial and temporal features from the spectrographs, which we found not only to aid in accuracy, but reduced overfitting during training and allowed for variable input into the detection model.
And so the CNN layer identifies the unique spatial patterns of a gunshot, while the RNN or the LSTM layers inside the RNN captures the temporal dynamics, which is crucial for detecting these short, high-intensity sounds.
Yeah, so this combination allows our model to recognize both the signature of a gunshot and the way its features evolve, gradually enhancing our detection accuracy. With a short time frame sound like a gunshot, this method extracts as much information as possible.
And of course, all models need training data. However, one major challenge was an imbalance in our data sets. Gunshot samples, for example, are far more authentic gunshot samples are far rarer than other samples. And obviously, when training a machine learning model, you want all classes to be equally represented. Otherwise, it could lead to poor detection performance for these critical events, as well as bias. To solve this, we implemented inverse frequency weighting. Instead of relying solely on data augmentation, as other research papers or state-of-the-art methods use, which can sometimes introduce additional bias. Instead, we assign higher weights to underrepresented classes like these gunshots during training. This approach makes errors on gunshots samples more significant, forcing the model to learn these features better. Additionally, we use data augmentation techniques like random cropping and time shifting to enhance the diversity of our dataset without distorting the actual sound.
Yeah, the combined effect of these strategies is impressive. Our model achieves up to 95% detection accuracy for gunshots, with recall rates around 98%, a performance that surpasses many state-of-the-art models. And it's not just about detecting gunshots. You mentioned earlier that the same model architecture can be adapted for other emergency audio detections, like car crashes or even pipe leak detection.
Exactly. As you might have noticed, none of these traits are specifically tailored to gunshots. This could be adapted to other audio event recognition cases. Hi, welcome to our live demonstration of the gunshot detection system.
So before we go into our live demo, let me just show you a few components that we have that make our system a whole. First, we have our speaker, which is connected to the Raspberry Pi over USB-C. Once the Raspberry Pi, which is inside the case itself, detects a gunshot sound and is confirmed in our app through a peer confirmation system, the speaker will then display an alarm sound. To constantly capture input audio waves, we are using a microphone that is placed at the top of the module right here. We went through countless iterations to ensure that the placement of the microphones and the placement of the speaker and Raspberry Pi were safe and optimal. Finally, to power this entire module, we can use both a battery-powered case, or we can directly connect the Raspberry Pi to a 5-volt power source, and there's mounting holes in the back of the system to be mounted directly to walls.
Great. Now let's move on to the demonstration. For this demonstration, we will be using a sound of a dog barking. The reason we chose this sound is because, similar to a gunshot, it is both short-term sounds and it is high frequency and very loud. And so this is to show that the gunshot detection system can differentiate between sounds like a balloon popping, a dog barking, a stack of books being dropped from a high place. So now we are about to play the sound. And as you can see, the alarm did not go off. But now to test a actual gunshot sound, just using any sample of a sound from the internet. as you can see, the gunshot detection system went off.
Thank you.
Thank you.